Why don't we begin? Good morning, afternoon, and evening to everyone here from all over the world. My name is Vala Fatemi. I'm here to welcome you on behalf of the entire organizing team of the Virtual Science Forum. We are largely a team of physicists who are volunteering to develop this free and open access virtual conference initiative. And we hope that this will serve to make conferencing more accessible to all scientists and also less taxing on our environment. If anyone here is interested in joining the effort, please see the links in the chat about ways to contribute. I'll post them again now. And I want to note that in particular, we are seeking volunteers that have some web development skills to help us on that front. And regarding our events, currently we are focusing on two types. The first are short conferences of 3 to 6 speakers that, like our inaugural conference, which you can find at our YouTube channel, like that one. So you can see that for an example of such a format. These are all open to the public. They're free. And also, as I noted, they're recorded and posted online so that they can be accessed in posterity. Moving forward, we are seeking motivated people who would like to organize conferences like that one on specialized and timely topics. And on our website, you can find our organizing guide and also a brief form on our GitHub page that lets you suggest such a conference to us. The second type of event is this one, our so-called long-range colloquium, which we've named in the spirit of extending the length scale of strong interactions and entanglement among scientists around the world. For the moment, this colloquium series will focus on developments in condensed matter physics and quantum information science. And the seminars are currently planned to be every other Wednesday at 1:30 p.m. Eastern Standard Time. Okay, and we all hope that many of those you who are here now will be able to contribute, which you can do by helping developing ideas and tools, organizing sessions, like I've mentioned, attending like you're doing now, and especially giving us feedback on your experience. The best way to provide feedback is on our GitHub page, which you can find linked in the chat. Finally, I would like to acknowledge support from TU Delft and Indiana University. And with that, I will now transition to this seminar's host, Anton Akhmarov, who will introduce both the format of our talk and our speaker.
All right, good afternoon, everyone. My name is Anton Akhmarov, and I'm a researcher at Delft University of Technology. It is my pleasure to kickstart this colloquium series with Liang from MIT, whom I believe vast majority of you already knows from his many contributions to the fields of topological insulators and broader fields of condensed matter. Today, Liang is going to talk about charge transfer excitations, pair density waves, and superconductivity in Moiré materials. Now, before we begin, just one final remark. This is we do want our events to be interactive. So please, we do invite you to ask questions. The way to do so is the following. When you have a question, please click on the participant list in the bottom of your Zoom window. And then you will see a button that says raise a hand. When I see that a question arises, I will unmute the person who wants to ask a question and invite them to ask the question. With that, I give the floor to Liang.
So let me first share my screen. Can people see my computer screen here?
Yep, loud and clear.
Okay, wonderful. Okay, wonderful. Okay. So good morning and good afternoon, good evening, everyone. So I'd like to start by thanking the organizers. These are really wonderful people that created this new format for this online physics conference, seminars, etc. And I'm sure that just many of us, we all hope that this virtual science forum continues well into the future. to provide a very strong forum for our community. And I myself is very honored to give this talk here. Okay, so let me start my screen. Okay, so today I'm going to talk about some new work on Moiré materials. It's about the charge transfer physics as a way to obtain a pairing in a purely electronic manner. So this work would not be possible without collaboration with these wonderful people. And the first part of this talk about the electronic structure of transition metal dichalcogenide marine materials is done with my group at MIT, Noah Yuan, Yang Zhang, and Tongdong Liu. And then the second part of this work, which is perhaps more interesting, perhaps more outrageous, is done in collaboration with Kevin Slago at Caltech. Okay. And as Anton said, please feel free to interrupt, ask questions. Okay. How does this work? Let me see. Okay, good. So so one topic in condensed matter physics has perhaps the most appeal to many of us. This is about superconductivity. Pairing how electrons form into Cooper pairs and how Cooper pairs condense to give rise to superconductivity. And one of the long-standing puzzles in the field is the so-called high-temperature superconductivity in copper oxide materials in cuprates. And then here, shown here is a schematic phase diagram. So unlike an ordinary superconductor that comes out of a normal metal, in these cuprates, the underlying state is an antiferromagnetic insulator, and upon doping, a superconductivity state appears in a range of dopings with a maximum Tc. But there are other parts of this phase diagram that is equally interesting. The superconducting state seems to grow out of an unconventional state, a so-called pseudo-gap phase, and et cetera, et cetera. So this is a pretty much simplified phase diagram of the cuprates, and has long been a mystery to understand this. And so starting from about 2 years ago, there's this new breakthrough coming from my colleague Pablo Herrera's group at MIT. These are magic angle graphene, 2 sheets of graphene with a specific twist angle around 1.1 degree. And here you see that a wide variety of unexpected phases appear, including Moire-like insulating states, as well as superconducting domes, which has certain similarities to this cuprate phase diagram. Okay, so so this field has been evolving extremely rapidly. A year later, this is work from Feshbach's group in Spain, and again magic angle graphene. But now we see that the phase diagram has certain similarities, but also differences. We see that insulating states appear at all integer fittings, and they are separated by the superconducting domes. So if you look at this, perhaps it's not that close to the phase diagram of the cuprates. And even more surprisingly, again, this work coming out of very rapidly, it appears that when the magic angle graphene is aligned with the boron nitride substrate, an integer quantum Hall effect appears without any external magnetic field, the so-called Chern insulating states. And this is totally different from the case of cuprates. So, with this, the talk is not neither about cuprates nor about twisted bilayer graphene. It's about an attempt to find some interesting physics in the simplest kind of Moiré materials. Okay, and it's about. So we'd like to ask a question. What are the core component of correlated physics in Moiré materials, and what are the additional features. So in a sense, we want to eliminate ingredients as much as we can and just deal with various bones. So this is what I want to tell you about. It's about Moire materials, not based on graphene, but based on transition metal dichalcogenides. And we will see that as the simplest kind of Moire material, it still has a lot to offer. Let me start with describing these materials. So in the monolayer form, these transition metal dichalcogenide are large gap semiconductors with a band gap of about 1.5 electron volt. One of the key feature is that the valence band has a strong spin splitting due to the spin-orbital interaction. And in particular, the topmost valence bands are located at the corners of the Brillouin zone, the K and K prime point. And within each valley, the spin is fully polarized out of the plane. And the two valleys have opposite spin polarization. This is a phenomenon known as spin valley locking. And this is what the structure looks like. If you view it from the top, these metal atoms form a layer of triangle lattice. And then these chalcogenide atoms arrange themselves in the plane above and below. So viewed from the top, you get a honeycomb lattice consisting of the transition metal atoms and two chalcogenide atoms that are vertically on top of each other. And at low density, when we dope the material into the valence bands, the Hamiltonian for the effective Hamiltonian for the doped holes is very simple. It consists of the kinetic energy, which is just p squared over 2m, because the bands near the valence band top are parabolic, and these holes interact with each other through the Coulomb interaction. So it's E squared over R. And in this case, because of the spin valley locking, they are only spin or valley degrees of freedom, but not both, right? So in terms of the number of degrees of freedom, it's 2 instead of 4. So this is perhaps the simplest realization of the uniform electron gas, right, in 2 dimensions. In this case, it's uniform whole gas. And the effective mass is about half of the electron mass for this material, tungsten diselenide. And just to show the rapid progress that has been made in improving the material quality, this is a very recent work from the Columbia group. And they studied this monolayer transition metal dichalcogenide under a perpendicular magnetic field. And as you can see from this results here, this is a capacitance measurement. And you see all these beautiful lambda levels associated with holes. And a magnetic field also couples to the valley pseudo spin. So the valley degeneracy is broken. So we get quantum Hall states at all integer fittings, both even and odd fittings. And moreover, you see all these sequence of fractional states that shows up. Okay, it's a testament of the amazing material quality that are now available. Okay, so I'm going to describe the Moiré superlattice, and out of these TMD materials, and this can be made, for example, by taking 2 different Moiré materials with a lattice mismatch. So in this example, this is tungsten diselenide and tungsten disulfide. They have a 4% lattice mismatch. So in without any twist angle, aligned WSE2 and WS2 already naturally form a Moiré superlattice. And in this case, the Moiré period is about 8 nanometers. And so here, the schematic figure shown on the right shows the band alignment of the 2 layers. And we see that the top most valence bands are in the WSE2 layer. So in other words, if we have a small amount of doping, the holes, they live on the WSE2 layer. Okay. Now what the other layer does is to modify the electronic property to form an electronic superlattice, to turn the holes in WSE2 layer into an electronic superlattice. And this is seen early on from STM experiments on WSE2, MOS2, a slightly different combination of materials. And what's shown here is a topography image. And you see that depending on where you are within this Moiré unit cell, there are different local stacking arrangement. And the height, the separation between the two layers depend on the local arrangement, local stackings, as well as the electronic spectrum. So shown here are the STM tunneling spectrum. And here, for example, you can see that the valence band edge is spatially modulated by the Moiré pattern, and the maximum of the valence band edge appears at the local AA stacking where the two layers are aligned. Okay, so in particular, the AA region and the AB region, so-called APW region in this notation, are going to be the important for our discussion later. So, so because of the valence band edge is spatially modulated, this can be captured by a long wavelength continuum theory introduced by Fengchen Wu, Alan MacDonald, and their collaborators about 2 years ago. And this is, again, the crystal structure of the Moiré superlattice. And there's a A region, AB region, and BA regions. These are the high symmetry points in the real space within the Moiré unit cell. And the periodic modulation of the valence band top can be captured by a long wavelength Moiré potential. And because the superlattice has threefold rotation symmetry, a periodic potential can be expanded into a sum of three Fourier components, the three lowest Fourier components. And the V0 is the strength of this potential, and G is the reciprocal lattice of the superlattice, reciprocal vector of the superlattice, and there's an important parameter phi, which determines the shape of the Moiré potential. We will come to it in a minute. But here, this is a calculation based on this continuum model, and you can see that there's instead of simple parabolic bands, this band breaks up into many mini bands, and these are the Moiré bands. And for example, here in this example, the lowest Moiré bands is separated by a gap of about more than 10 millielectron volt from the next bands. Okay. So, so very recently, there's two, I think, pretty remarkable experiments. So first one is from Cornell group, and they look at this tungsten dicyanide, tungsten disulfide, and as you dope the holes into the Moiré bands, you see that when the Moiré band is completely filled by 2 holes per unit cell, an insulating state appears. This is what we expect for a band insulator with a complete filling of bands. But at half of that filling, with 1 hole per Moiré unit cell, another insulating state appears. That was described in this work as mod insulator. Certainly, it's a correlated insulating state which appears at low temperature.
Liang,
yeah.
How did they actually determine the filling here? Do you happen to know?
Yes. So so the question is about so the filling is inferred from the area of the Moiré unit cell and the gate voltage. And now what's interesting that in these TMD materials, the alignment between the 2 layers have been measured through the second harmonic generation. So so in this, I think in both of these experimental works, so you have 2 layers and WSE2 and WS2, they overlap in some region to form this heterobilayer, but they also extend right into their own regions. So these are experimental groups. They measure the second harmonic generation on the WSE2 layer and on the WS2 layer separately. And by looking at the polarization dependence of the second harmonic generation signal, they can infer the alignment of the angles. And it turned out that the alignment is essentially it's a zero twist angle within some uncertainty less than 1 degree. And that gives you an idea of the Moiré area. So you know the Moiré area and you know the charge density, and you can convert it into the fittings. Yeah. Okay, so this is another experiment coming around the same time from the Berkeley group. And again, they used some kind of optical methods to detect the resistive states. And not only at the half fitting, when you have 1 hole per unit cell, there's some insulating states, it's correlated insulating states. But also you see that at fractional fitting, when the number of holes is less than 1, when there's fitting is 1/3 or 2/3, these insulating states appear. So these are believed or proposed to be charge density waves. For example, at 1/3 fitting, you have this charge form a superlattice, a triangular superlattice, and at 2/3 fitting, you can think of it as the missing holes form a superlattice, right? You can think of it as a density waves, or you can think of it as Wigner crystals being pinned by the underlying Moiré lattice. So this already tells us that the physics of these TMD heterobilayers are very rich and quite different from twisted bilayer graphene. In twisted bilayer graphene, at least so far, all the insulating states are only seen at integer fitting. Okay, so this provides a motivation for us to look into the physics of these materials. And so in a way, I like to think of these TMD Moiré superlattices as some kind of a magnified crystals, right? So the low energy Hamiltonian is the kinetic energy, the Coulomb interaction, and a periodic potential, right? Just like the natural solids. But in natural solids, this periodic potential is the singular Coulomb potential coming from an array of ions with atomic angstrom spacing. Yes, question? Question? Okay. So this Coulomb potential is highly singular, and for a given solid, right? The nature gives us the atoms, the crystal structures. It's not possible to tune it very much. On the other hand, if you look at this TMD Moiré superlattice, again we have kinetic energy with Coulomb interaction, but now instead of Coulomb potential, we have a smooth, slowly varying Moiré potential, which is nothing but sinusoidal potential. And in this case, one can tune the strength of correlation by the twist angle. As you move away from 0 degree, the Moiré period decreases, so the effect of the potential becomes small compared to the kinetic energy. So large period means strong correlation, okay, because the kinetic energy of the Moiré band decreases. Moreover, this potential strength V0, it is material dependent, and it can be tuned also by applying pressure. And this phi is actually the key parameter that I'm going to focus on. So when you take a sum of 3 cosines, take the sum of 3 Fourier components, there is an overall phase that determines the shape of this potential. Let's see, does this work? I got stuck here. Can people still hear me?
Yeah, we can hear you, but indeed the slide transition didn't work.
Yeah. Okay. Okay. So so this is what I'm going to focus on. I'm going to focus on physics as contained in this universal Hamiltonian for TMD Moiré superlattice. So the first thing we look at is look at the electronic structure, single particle non-interacting band structure more carefully for this material WS2, and using the DFT calculation for a twist angle about 6 degrees with more than 600 atoms per unit cell, we can obtain the DFT band structure showing these dots here, and fitting this DFT band structure with this continuum model with the cosine potential, it will tell us the potential strength and this Moiré potential parameter phi. So the strength is 15 milli-electron volt. The parameter phi is about 45 degrees. And when we plot this Moiré potential, you notice that this potential has a primary minimum. So here I'm thinking of this potential for the holes. Okay, for the holes. So the first band corresponds to are dominated by holes that are localized in the minimum of the potential. Okay, but here, interestingly, there are two types of potential minimums. The primary minimum is located in the AA stacking region, local AA stacking region, and the secondary minimum are located in the local AB stacking region. So, so in this figure, the primary minimum is here, it is dark spot, and the second potential minimum is here. Okay. So use this once we extracted these Moiré potentials. This allows us to calculate the non-interacting band structure at larger Moiré period. Okay, so with 8 nanometer periodicity, unit cell consists about 10,000 atoms, so it's impossible to do a DFT calculation. But now we can look at the continuum model with the parameters extracted from DFT at a smaller twist angle, a smaller period. Okay, so in this case, we see that as the Moiré period increases, the band becomes much flatter, right? The bandwidth is reduced to about only 8 milli-electron volt. The first and second bands are separated by a gap about 18 milli-electron volt. And when we look at, for example, the first two bands, the linear functions are very well localized in the primary and secondary minimum. Okay, in the A region and in the AB region. The size of the linear orbitals is about 2 or 3 nanometers, smaller, considerably smaller than the period. So really, what we should think of is that although this Moiré material has 10,000 atoms per unit cell, in terms of its low energy electronic property, one should just think of it as being like a diatomic crystal, right? There's one type of atom in the A region, it has a S wave-like linear orbital, and there's another set of atom in the AB region. And if you take these two atoms together, they span a honeycomb lattice. So this gives us our low energy description. It's a honeycomb model formed by two types of atoms. One can think of it as cations and anions. And we have hoppings between these sites. The two atoms have different on-site potentials, which we call delta. There's an interaction, both the on-site interaction, which we call U, and there's a extended interaction between first neighbor, second neighbor, etc. Okay, so here, with a Coulomb interaction, it's long range, it's 1 over R. It decays very slowly. In real experiments, there's often metallic gates nearby. So in that case, the interaction is screened at long distance when the distance exceeds, when the separation of two charges exceeds the distance to metallic gates. So this is basically now we get a honeycomb extended Hubbard model. Okay, and these are the energy scales in this problem. So with this Coulomb interaction, we get the on-site Hubbard U is about 150 milli-electron volt. The nearest neighbor repulsion is about 50 milli-electron volt. And at even larger separation, the interaction decays exponentially when there's both top and bottom gates around. And you can see that the interaction calculated using the linear functions. Yes?
Just a moment, there is a question. Please go ahead.
Yeah, hi. So when you spoke about the Wannier orbitals, it seems like unlike the case of crystallize graphene, these Wannier orbitals do not have that fidget spinner-like structure. They're just basically S-like orbitals.
Absolutely.
Sorry?
Yeah, you're absolutely right. That's correct.
And could you shed some light on why one should expect this intuitively and how one will have a transition as one takes a model of this two transitional metal dichalcogenide and somehow tunes parameters to make the model approach crystallize graphene?
So the two
or is that not possible? Is that not even possible?
Yeah, they are very different for the following reason. That in the TMDs, we start the underlying material in monolayer form has only parabolic bands. Right? So what we are dealing with is just parabolic bands in the presence of a pure potential. And when the potential is deep, then you naturally expect states are localized near the potential minimum. And this is exactly what happens at large Moiré resistance. Right. So when you have this is essentially the first problem we learned in solid state theory, right? You have a particle in the periodic potential with a sinusoidal potential. If the potential is weak, we're in the nearly free electron limit. And that is what happens at this twist angle about 6 degrees. You see the bands are almost like the free particle bands, but now folded into the mini Brillouin zone and with a small anti-crossing at the Brillouin zone corners, Brillouin zone edges. This is a nearly free electron limit. But you take the same model, but now when the Moiré period increases, effectively speaking, the kinetic energy becomes small compared to the potential energy. Now we are in the deep potential limit. So what we get is a tight binding limit, right? We get this localized linear orbitals. So all these are much simpler than the twist graphene. This is why I want to find the simplest material possible. The twist graphene, the complexity arises because we start with Dirac particles, right? The low energy charge carriers in each layer of graphene are Dirac particles, not the Schrodinger particles. Okay, good. Yeah, all right. So, so this is the energy scale associated with interactions and this energy difference between the cation and anion, which we call the charge transfer energy, is about 15 milletron volt. The bandwidth is the smallest energy scale. It's only about 8 milletron volt. Okay, so interaction dominates, and also the on-site interaction is much larger than the first neighbor interaction. Okay, so what we end up with is a strong coupling limit. And this limit appears to be extremely simple, right? So if we completely neglect the quantum tunneling, the hopping between different sites, we end up with just a Coulomb system of charges on the honeycomb lattice, right? So this is almost completely classical, not quite in the following sense. The quantum mechanics are important. So in the sense that these charges, they occupy winding orbitals. So the position of the charge are tied to the point on the lattice. If you have a completely classical system, then the position of the charges can take continuum values. So aside from that, we end up with just a charge on the lattice with Coulomb interaction between them. Okay. So is there still anything interesting left for this system? And it turned out, okay, so just to show that in this picture, it becomes immediately clear why this charge order states appear at fractional fitting. So again, you take this classical limit, turning off the hopping between sites. And so this is a Monte Carlo simulation in this classical limit by Tongtong Liu. And you see that the 1/3 and 2/3 fitting, the electrostatic repulsion energy is minimized when charges form these density waves, which enlarge the unit cell by a factor of 3. Okay, and in this case, the charges only occupy the anion sites. Basically, so there are two. The system we're dealing with on the honeycomb lattice with 2 sublattices, right? The one that has a lower on-site energy, we call that anion, and when the fitting is less than 1, all the charges goes to these anion sites. So that's why here I'm only showing the triangular sublattice of the honeycomb. And also, to understand why these density waves appear, it's become very natural if you think about extended interactions, right? So, for example, at 1/3 fitting, this pattern shown on the left, it avoids the nearest neighbor repulsion. Right? So this is the closest packing without causing the nearest neighbor repulsion. So these examples show you that the extended interaction are actually important in this material. Okay, so Let me now move on to the next slide. Having some difficulty flipping through the slides. Okay, so now let us consider increasing the filling to n equal 1 when we have a 1 charge per unit cell on the Huntington lattice. And in this case, obviously the charge should go into occupy the anion sites. So we have 1 charge per anion sites, right? This corresponds to the local AA stacking region. And then 2 types of insulating states have been discussed in the literature, long before. And in both cases, right, the charge are in the anion sites, but they are distinct, and they are called by name of mod insulator versus the charge transfer insulator. They are different from each other when we consider the excitations. What happens if we add an extra charge into the system? So in the case of mod insulators, it appears when the other site, the cation sites, has a much higher energy. So when an extra charge is added, this charge prefers to go to the AA site to form a double occupancy. So this added charge creates double occupancy, costs energy U, while the occupying the cation sites costs even larger energy. Okay, so in this description, then the AB site, the cation sites, can be completely neglected. So we're just dealing with basically a single band Hubbard model, and this is a mod physics. On the other hand, if the energy difference between cation and anion is small compared to the on-site Hubbard U, then doped charge prefer go to the cation sites. Okay, so the added charge now occupy a different types of atom, and in this way, it avoids double occupancy. Okay, so this is the so-called the charge transfer insulator. So it's all very simple that when the Hubbard U is too large, the system would rather occupy a different atom to avoid double occupancy. And this, we think, is the case for these TMD materials. The next slide. Okay, so let me also let me mention that this charge transfer insulating states has been discussed a lot in the context of cuprates. In cuprates, there's a copper and oxygen atoms. They are the analog of what I call cation and anions. And again, in this case, because of the large on-site repulsion associated with the copper d orbitals, doped holes prefer to go to the oxygen site. So the energy gap to charge excitations is a charge transfer gap rather than the Hubbard U. Also, I want to mention that this charge transfer effect has also been discussed in the context of twist bilayer graphene by these people. These are some inspiration for our work. So, so when we look at this TMDs, we plugged in the numbers. Let's see, next slide. Does this work? Okay, so when we look at the numbers here, so one can ask question, what is the charge gap in this charge transfer picture? So this charge gap is defined as the energy cost of adding electron and the energy cost of the removing electron. The sum of the two defines the charge transfer gap, and the added electron goes into the cation site and removing electron from the anion sites. So when we take both into account, the charge gap is about 60 millectron volt. This is the same order of magnitude as found in experiments. On the other hand, in the mod picture, if the extra charge double occupy the anion sites, then this charge gap would be much bigger, would be several hundreds of millectron volt. So this gives us evidence that the system is really a charge transfer insulator. This TMD heterobilayers at half filling is really a charge transfer insulator rather than a mod insulator. So now let me move on to the second part of this talk. So, so I hope so far everything is pretty straightforward. Okay, so now let me move on to the second part of this talk. So based on this charge transfer physics with Kelvin Slago, we propose that pairing can occur when the system doped to the filling above 1. Okay, and this work is posted in the archive. And I would like to thank, we benefit from discussion with a lot of people, but in particular with Steve Kivelson at the early stage of this project. Okay, so let me now just do some simple physics. Let us consider the energy cost of adding 1 electron to the system. Again, we are in the strong coupling limit. We neglect the quantum hopping between sites. So this is a classical electrostatic problem. Let's see, slides have been having difficulty. So let me look at here. I see I'm missing one slide. I can use this here. Okay, so can you still see my screen? Can people see my screen? Okay, great. Yeah. So let's consider the energy cost of adding 1 charge, right, to this cation site. Let's call that energy E1. So this is nothing but delta, which is the on-site energy difference, on-site energy cost of this cation site, plus the nearest neighbor interactions between its 3 neighbors, which I call 3 times V1, plus longer range interactions, right? That's clear? Now, let's consider the energy cost of adding 2 charges that are far apart from each other. And that is just twice the energy before. So it's 2 times delta plus 6 times V1. Bringing these 2 charges together costs more energy, right? Because now there's extended interaction, second neighbor interaction between them, which I call V2. So that's not favorable at all. But let's now imagine, let's now look at this alternative scenario. So when we bring 2 charges close to each other, at the same time, we transfer a background anion charge to the neighboring cation site. So we form an object which consists of 3 charges around a vacancy, or you can think of it as 2 added charges bound to a charge transfer dipole. So I have transferred a charge in the background to a cation site. Okay, so in this case, let's consider what is the energy cost of this object. So this object has a net charge of 2e compared to the n equal 1 insulating states, and we call this a trimer. Now I'm in difficulty flipping through the slides. Let me try. Okay, so maybe I just.
Why does this have charge 2e?
Because I've added 2 charges, right, to the system. So compared to the reference state, the reference state is when there's 1 charge per anion site. Compared to that, I added 2 extra charges to the system, and I transfer an existing charge to a neighboring place, right? So this object has a net charge of 2e compared to the state I started with. Clear? Okay, so so this is the energy cost. So now there are 3 charges on the cation site, so the cost energy is 3 delta. Each added charge, each of these charges on the cation sites has 2 nearest neighbors. So in total, I have 6 nearest neighbors, just as the case of 2 charges far apart from each other. So when we have 2 charges far apart and without creating any charge transfer dipole, we have a energy cost of 6 V1. So the same happens here, okay? But now we see that there's an energy gain associated with the second neighbor repulsion. So previously, we have a charge in this background here. It has 6 second neighbors, right? So once this charge has been removed, we gain back 6 V2. But at the same time, there are 3 nearest second neighbor repulsions, right, between these charges here. So I put back 3. So net gain is 3 times V2. Okay, is clear? It's a purely electrostatic, right? Electrostatic problem. So now if I compare the energy cost of this trimer and the charge of 2 charges that are far apart from each other, the energy difference is 1 delta minus 3 times the second neighbor repulsion V2. And you can take into account the longer range interactions represented by these dots here. Okay. So the important thing is now this energy cost can be negative. Okay, this energy cost can be negative when the charge transfer energy delta is small. This quantity will be negative. Okay, in other words, by forming this trimer, which has a net charge of 2e, it actually costs less energy. It can cost less energy than 2 charges that are far apart. Okay, so what's interesting here is that all the 2-body interactions between charges are repulsive, and the physics here is completely classical. We're just dealing with a collection of charge with 2-body repulsion between them, and yet that we find that when you add 2 charge to the system, they may energetically prefer to bind together and to lower the total electrostatic energy. So in this sense, less repulsion is attraction, right? And this only works because 2 added charges can polarize their surroundings, meaning that they can create a charge transfer dipole and bind themselves to this charge transfer dipole to form this.
Yeah, there is another question, please.
Liang, this is Andrei Nevedomsky. Quick question. So why does V2 enter with a minus sign?
Oh, it's because,
Is the interaction repulsive?
Right, so V2 is repulsive, yeah. So we are comparing the energy, right? We are actually, I think there is a, sorry, this should be 3. My apologies. Yeah, here it's positive, but when I look at the energy difference, the energy difference between, thank you. The energy difference between the trimer and the state of 2 separate charges, then there is a 3 times V2. Actually, I think here it is, sorry. No, I take it back. It should be, I think when, actually, no, this is minus. So because what is the energy of the trimer? It is the energy of this configuration. The energy cost of a trimer is defined as, like in any, when we define any energy cost of any excitations, is defined as the configuration, the energy of the configuration with the excitation minus the energy of the state without the excitation, right? So if we look at the charge transfer insulating states, we had a charge on the center here, but we don't have the 3 charges surrounding it, right? And in that configuration, there are 6 V2, right? 6 V2s associated with the center charge. The total energy of the charge transfer insulator, it includes all the 2-body interactions between the charges. There are 6 V2 associated with that. Now, once we form a trimer, that 6 V2 has been released. It has been released. But at the same time, we create 3 new second neighbor interactions. So we put back 3. So the net result is I will get a minus 3 V2.
Excellent. Thanks.
Yeah. So it's it's high school physics. Okay. So so this is this is the key result. This is the key result. So basically, even in this classical system of charges with repulsive 2-body interactions between any 2 charges, what we see is that we can get pairing directly from the repulsion. And this pairing is non-retarded. We're not using any quantum mechanical effect, right? So, okay, so this will be so with this, then the rest becomes straightforward. So we can do the counting more carefully. So to include all interactions, not just first neighbor, second neighbor. So when all the interactions are included, this is a phase diagram. So it can be organized in this simple way. So the x-axis is the ratio of the second neighbor repulsion and the first neighbor repulsion. The vertical axis, ED, is the energy cost of creating a charge transfer dipole. Okay, so without any interaction, the energy cost of charge transfer dipole is just delta. But with the electrostatic interactions, it includes 2 times V1 and etc. 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 Okay, so all the long-range interactions, the effect of that is to renormalize the energy of this charge transfer dipole from delta to a new quantity which is called ED. Okay, so once we write the results in terms of ED, this phase diagram is exact for all kinds of interactions. So as long as the ground state at n equal 1 is this charge transfer insulating state, then this phase diagram is exact. So we see that in this different parameter range, what is shown here are the lowest energy per charge excitations. Okay, so we compare the energy cost of creating a single hole with half of the energy cost of creating a charge 2e trimer. Okay, and we see that in some parameter range, trimers cost less energy per charge compared to the hole, to a single charge. Okay, so remember that in this whole system, everything I'm talking about is in the charge that exists in the form of holes, right? So this is what we mean. Now there's also in some in this lower part of this parameter space, there's another type of a charge E excitation which has the lowest energy, and this is a electronic polaron. Again, has a charge E. You can think of that as a hole bind to a charge transfer dipole. Okay, so we're going to focus on this parameter range where the lowest energy excitations are trimers. Okay, and in terms of numbers, the electrostatic energy is a large quantity, but the binding energy, the energy difference between a trimer and 2 holes is actually a small quantity. Okay, so based on our estimates, it's shown here. It's about 30 millielectron volt divided by dielectric constant minus the charge transfer gap. So this quantity is probably on the order of 10 millielectron volt or even less. Okay, but the main result is that perhaps at least surprising to us is that in some parameter range, in this model with purely repulsive interactions, we can get binding of charge to lower the total energy. And the lowest energy excitation are charge 2e objects. Yes?
There's another question. Please go ahead.
Hi, Liang. 2 small questions. One, if this wasn't a hexagonal lattice, if it was like a square lattice, would you be able to play the same game with a different number mer? Like
I think what you need is probably a square lattice like the cuprate, right? Both copper and oxygen.
Right. So
probably you still need 2 types of atoms.
Okay.
Called cation and anions. Yeah.
And then what about some other local distortion? If you have these extra charge, like this added charge, could it, rather than fall into one of the...
Do you mean lattice distortion?
Yeah, that follows along from this, added charge. Could that ruin this game?
Yeah, that's a good question. So there's certainly something to consider. So here I'm not considering any lattice distortion, but I totally agree that the effect of lattice distortion it may or may not be important, but it's something to be considered. And right now I don't know in which way it goes. Does it make trimers even more favorable or make it less favorable? Yeah. So now, one thing I think that in this case lattice distortion may not be that bad. Let's say is the following: if you think about the situation we're dealing with here, each charge are spread out, right? The size of the winding orbitals is like 3 nanometers. nanometers. So perhaps the effect of the lattice distortion is not that big. Yeah.
I guess it's a question of scales, right?
Yeah, it's certainly something to consider in the future. Yeah.
I have a question. The interaction you're saying is not retarded.
That's right.
It's just static.
It's static. Yeah.
So why wouldn't the system just distort and form?
Because you have a deep periodic potential. So when you have a deep periodic potential, the Moiré potential, the Wiener functions, they occupy fixed regions.
Okay.
So this is what I mean. The system is not completely classical in that sense. The charge still occupy quantized area, right? Meaning, the charge still occupy orbitals, right? It's like atomic orbitals.
Right. Okay, so you're taking advantage of the pinning set
Absolutely.
up by the Moiré to maintain this
Absolutely.
static pairing interaction.
Absolutely, yeah.
So to my mind, then this seems to be just a Wigner crystal.
We'll come to that. Yeah, we'll come to that. Yeah, so far, yeah.
I have to go actually. So, but anyway, as long as you get to Wigner, then I'm fine.
Okay, sure, definitely. Definitely, yeah.
Sorry, also in view of time, I would propose to let Liang talk and then postpone the discussion to later.
Bye.
Yeah, I'll be quick. From the rest will be easy. Okay, so this is a Wigner crystal, Philip. Okay, okay. So here basically discuss energy excitations with lowest energy per charge. Right? This is still excitation at the fitting energy one. But now let us consider finite doping. Let us consider a small amount of doping, finite density but small. So in this case, then one expects, one would expect that when the doping is small, the ground state will be formed by these lowest energy charge excitations, and they want to avoid each other as much as they can. And in particular, let's suppose that the interaction, due to the screening by the metallic gates, has some finite range which we call R. At small doping, sufficient small doping, these low energy charge excitations can stay away from each other's interaction range R. Okay, no problem with that. But then as the fitting increases, there will be a critical density that corresponds to the densest packing such that the interparticle distance is still bigger than R. But we cannot go to a higher density. At an even higher density, then these particles, these charge excitations now have to interact with each other, which costs more energy, right? So at this densest packing, at the closest packing where the interparticle distance is still bigger than R, we would get an incompressible crystals, an incompressible Wigner crystal of the charge excitations. Okay, and so if the lowest energy excitation is just a single charge, then what we get is just a triangle Wigner crystal of these individual charges. And here I've shown a few examples at 1/7 filling, at 1/4 filling, at 1/3 filling. Okay, so these are essentially Wigner crystals, but they are pinned by the underlying Moiré lattice. Okay. On the other hand, remember that there is a parameter range where the lowest energy excitation, lowest energy per charge excitation is charge 2e trimers. And then if that's the case, on the small doping, right, on the small doping, we can get a density wave of these trimers, which are charge 2e pairs. So this is what we call the pair density wave. This is an insulating state of charge 2e pairs in the form of these trimers. And notice that they now occur at a different filling, right? At 1/8 filling, this is one example. And the closest packing of the trimers without costing any additional interaction up to the fourth neighbor, okay, is shown here. This occurs at 2/7 filling, at 2/7 filling. So 2/7 and 1/3 are very close to each other, but they are different. So now let us look at the experiments. And again, this is from the Berkeley group. They identify these peaks at fitting 1, 1/3, and 2/3. And the authors didn't really discuss features above n equal 1. This may well be artifact, but one certainly sees additional peaks. So, you know, Kevin took a close look at this data. And, you know, interestingly, at least you can say with a loving eye that he can identify these peaks, extra peaks. And you can see here that there's one extra peak, which is close to 1 + 1/3, but actually it's much closer to 1 + 2/7. Okay, this, I don't know if you can see it. Anyway, so perhaps this is a hint of some kind of a Pyrdance wave. We don't really know, but maybe it's something interesting to look after. Okay, so so Anton, can I have another maybe 5 minutes?
Yeah, please, by all means.
Okay, sounds good. Yeah. So okay, so so now let me come to the final part of this work, which is what happens when we turn hopping back. So far, everything I've described in the strong coupling limit, when the hopping is really small. So the system is basically a set of classical charges on the lattice, and we get density wave, you know, Wigner crystal states. But what about the effect of quantum mechanical hopping? So first, at this fitting n equal 1, the charge transfer insulating state, hopping induces spin exchange interaction. And to make my life easier, I'm going to consider an applied magnetic field so that spin are fully polarized. Okay, so this is totally different from the case of cuprate. In cuprate, the antiferromagnetic exchange interaction is very strong in the undoped case. However, in these TMD heterobilayers, experiments show that a small field less than 1 Tesla is already sufficient to fully polarize the spin. I won't discuss into detail of these results. So all I want to say is that from now on, I'm going to consider the fully polarized case. So the spin degrees of freedom are completely frozen. And we will see that yet something interesting still can happen, okay, in the fully spin polarized regime. So when we turn on the quantum mechanical hopping, it has several effects. First, the single charges, the doped holes, they now can hop around and they form a dispersive band. So because of the presence of the band, the energy cost of adding a delocalized hole is now lowered, right? It's lowered by the kinetic energy of this itinerant hole, okay? On the other hand, if we think about the trimers, because it is a composite excitation, to hop a trimer, it requires a third order process, right? So each charges that form this trimer has to hop individually, and therefore the hopping amplitude of a trimer is small. It's t to the power of third divided by the interaction energy v squared. So the hopping amplitude of trimers can be neglected to the leading order. Okay, so when the hopping is small, the bandwidth of individual holes is small compared to the binding energy. Then when you dope the system, the doped charge directly go into the trimers, which are charged 2e bosons. So we don't need to consider the effect of holes to leading order. And in this case, as I said before, the ground state can be a pair density wave at these commensurate fittings, or away from these fittings, the ground state can be a superfluid, a Bose condensate of these charged 2e trimers. This will be a very strong coupling picture. But I think the more interesting case is consider the increasing the hopping amplitude, and this can be achieved again by the twist angle. As we move away from 0 degree, the Moiré inner cell decreases, the hopping gets stronger, the bandwidth of holes increases, right? So as the bandwidth increases, the energy of this delocalized hole at the bottom of the band is getting lower and lower towards the energy cost of a trimer. And this is the regime that I want to focus on. So in this regime, the resonance happens. right? So when the energy of a delocalized hole at the bottom of the band approaches this energy of the trimer, trimer and hole interact resonantly with each other. This physics is very similar to the Feshbach resonance in atomic gas, right? So there is a conversion. A trimer can now convert into two holes, and this here illustrates how this conversion can happen. So one of the charges in the trimer hop back to the anion site, and this just leaves a state of a pair of holes, and they repel each other, so they tend to move away from each other. And through this second order stage, through this second order process, a trimer is converted into two weakly interacting holes. Okay, so again, for people in cold atom community, this is all very familiar. The only difference I want to highlight here is that in cold atom systems, a molecule is formed by just two atoms in free space. So it's a two-body physics. While here, trimer as a charge 2e excitation, it's made possible by this many-body vacuum, which is a charge transfer insulating state at n equal 1. Okay, so you take just two charges in free space, they always repel each other due to the Coulomb effect, Coulomb interaction. But the remarkable thing is that when we start with the charge transfer insulating state, add two actual holes, they can form a trimer, okay, in the right primary range. Okay, so so we can now describe the again go to the low energy limit, right? So if we have when we are in this regime, when the band bottom of the holes is close to the energy of the trimers, we can write down a low energy theory just involving the states near the band bottom. Okay, so in this case, if we go back to the original problem, that the neighboring hopping between the cation sites, the amplitude is positive. So this band of doped holes actually has two degenerate minimum at k and k prime points. Okay, so this we can call it a value pseudospin, and the conversion between the trimers into these two itinerant holes has this form that's dictated by symmetry. So plus and minus denotes the holes at two band minimums, plus k and minus k. So this pairing is valley singlet, okay, in the S wave channel. Okay, again, this is dictated by the symmetry. So let me skip the details for now. So this leads us to this universal model for doped charge transfer insulators. So we have psi, which labels the itinerant holes, and near the band bottom, they have a dispersion which is parabolic. They have a valley index. This phi denotes the trimers, and its energy relative to the bottom of the hole is denoted by epsilon naught. And there's a conversion that a trimer can be converted into a pair of holes. Okay. And finally, there is a electrostatic interaction between charges, right? The charge density is given by the sum of the charge of the holes and twice the number of trimers. Each trimer carries charge 2e. Okay, so this is our low energy Hamiltonian in the continuum limit. And again, so this is just stating the same thing again, that when the detuning is negative and large, when the trimers are lowest energy excitation, the ground state is just charge 2e bosons, which is either superfluid or Wiener crystal. But as they are brought to resonance, when the detuning approaches zero, the scattering length diverges. So in this case, the resonance in process, the conversion between the trimers and holes always dominates over the Coulomb repulsion. Okay, and this is the key of resonance physics. Near the resonance, the scattering length diverges, and this physics is universally described by the BEC and BCS crossover, just like in the cold atom gas. So this resonant interaction between the holes and trimers leads to a superconducting ground state. Okay. So finally, that if detuning is large and positive, then the band bottom of holes is below the trimer energy. In this case, as you start dope the system, you first form some Fermi liquid states, and as the doping increases, the Fermi level approaches this trimer resonance, and then this resonance process again leads to superconductivity. Okay, so the difference is that if the system is tuned close to resonance, when the trimer energy is close to the bottom of the whole band, then immediately upon doping, the system changes from a charge transfer insulator immediately to a superconducting state. Okay, while in this second scenario, when the detuning is now positive, the system starts being a Fermi liquid upon doping, and only above a critical doping, it becomes superconducting. Okay, so this is essentially everything. Let me summarize it here. So in terms of the, hopefully I described to you some of the interesting physics that still needs to be seen in transition metal dichalcogenide heterobilayers. Starting from this Moire superlattice, we see that there are two types of potential minimums in the A region and AB region. So that's why the low energy physics is that of a diatomic crystal with a cation and anion. And because the energy difference between the two atoms is small, the system at half filling is a charge transfer insulator, and the doped charges go into the cation sites. Now, I've shown you that despite the two-body repulsion, two-body induction is purely repulsive, that a trimer can be formed, which is a charge 2e object, and this pairing is possible because the system can lower its electrostatic repulsion. Okay, in a very, very simple way. When the kinetic energy of the holes is small, these trimers can form insulating density wave states, a Wigner crystal of trimers. Alternatively, if the kinetic energy of the holes is large, holes and trimers can coexist, and they can interact resonantly with each other to form superconductivity. Okay, and here the superconductivity appears even in the spin polarized regime. Okay, so the pairing mechanism is not based on the spin degree freedom, but based on the charge. Okay, and the resonant superconducting state is similar to the BCS crossover, and in future one can expect a lot of more interesting pseudo gaps, strange metals, etc. So with that, I'm going to stop, and I'd like to thank my collaborators again, and thank you.
Thank you very much. All right, yes, we're not going to go with the applause, but I see people applauding and well, clicking on the applaud emoji. So let's, I also see some questions, and we do have a bit of time still. So let's see, I see there's a question from Nader Mostan.
Yeah, so my question was that about this hopping that induces exchange interaction. So if you didn't turn on this magnetic field, so what would be the magnetic state of the Wigner crystal? So is it like ferromagnetic or anti-ferromagnetic or what?
Wigner crystal or of the charge transfer insulator, which filling?
Okay, so let's say a half filling.
Right, at n equal 1, right? Yeah, that's actually an excellent question. So that really, I think, depends. There are several exchange processes one need to take into account. Well, there could be a direct exchange, right? That, for example, if you look at, let me go back to the case of n equal 1. That's a very good question. Right. At n equal 1, right? So you could have a direct exchange, right? This charge hops to here and hop back, right? Or one can have a super exchange, right? For example, a charge hops to here, this charge hops to here, and this charge goes here, right? So it really depends on the magnitude, right? The relative magnitude of these different exchange processes. This is something that we are still studying.
Yeah, thanks.
But whatever it is, what is clear is that the energy scale associated with exchange interaction at half filling is small. It's so small that that a very small field is already sufficient to fully polarize it. Yeah.
All right, I see there's another question from Raquel Queiroz.
Hi. So in twisted bilayer graphene, there's spontaneous C3 symmetry breaking that is seen in STM. How would that compete with the order that you have here? Because there's the pinning of the locations of the Vanier centers depends on the C3 symmetry. Would that?
So here, what I can say is that so for example, in the case of this, so I think this is a good question. I think there's one way to experimentally settle with this issue, which is again second harmonic generation. Right. The good thing about TMD is that it has a very large second harmonic response. So, for example, in the undoped case, the second harmonic generation shows threefold symmetry. So now one can ask the question that if you dope holes into the system, is the threefold symmetry still present? Right. So this could be an experimental way of addressing this question. So so I think in our picture, at half filling, right? I think the half filling state is really very simple. It's just you have one charge per anion site, and this state is threefold symmetric.
Thank you.
You can have perhaps symmetry breaking at other fillings, but at the unequal one filling, I think the charge transfer insulating state is quite robust.
All right, I see there is a question from Andrei Nemedovsky.
Hi, Liang. The question I have is about, so everything you told us in the second part of the talk applies assuming you have this charge transfer insulator as the vacuum state. Now, as you mentioned, the delta, the typical scale of that charge transfer is about 15 MeV. You have a sense of, so, obviously that depends on the material and the details, but do you have a sense of when all the energy scales essentially need to be smaller than that scale, about 15 MeV? Can this delta be tuned by changing the angle or the lattice mistake?
So I think it may depend on angle weakly, but what it will certainly depend on is pressure. Yeah, I think pressure will be a very good way of increasing the energy scale in the problem. So as you apply pressure, I think the potential, the Moiré potential becomes deeper. When the Moiré potential becomes deeper, you can go to the strong coupling regime at a smaller Moiré period. Okay, and when the Moiré period decreases, the characteristic interaction energy E squared over L become larger. Yeah, so I think pressure might be a good way of tuning increasing the energy scales in the problem.
Right. Thanks.
At least if I think that in twisted bilayer graphene, for example, right there, it's shown that even if you are away from the magic angle, even when the band you start with are not so flat, then applying pressure increases interlayer tunneling, which increases increases correlation, flattens the bands. So I expect something like that, maybe at work here. Yeah.
All right. I see there's another question from William Vano.
Yeah, so I would like to ask you about these two charges when they are far away from each other, and eventually as they form trimer, basically they lower their energy. So one could say that there's basically an attractive potential between them. And yeah. So, but what about the long range? So when they are really far away from each other, would this potential be repulsive or?
Oh yeah, when they are, so in the case, if the Coulomb interaction is unstreamed by the metallic gates, when they are far away, they are, they are small but still repulsive. If they are screening from the gates, when the separation between two charges are larger than the distance, sufficient large compared to distance to gates, these two charges are essentially not interacting. Right? But it's always either repulsive or essentially zero, a large distance.
Because if there was like large repulsive interactions, also like let's say 3 sides distance, then it might lead to different physics, like increasing the, let's say it would form like triangular lattice or something, just by repulsion. Okay, thanks.
Okay, fine.
Yeah, I mean, if there was like strong repulsive interaction, like on when they are not too far away from each other, it could lead to different ground states.
I mean, are you talking about just 2 charges, or are you talking about a finite density of charges?
Yeah, if you just increase the number of charges in lattice.
So for example,
With repulsive interaction.
Maybe you ask me this. So you know, for example, in the strong coupling limit, right? So I talked about various density wave states. So this picture, right? This approach I'm taking here, right? It always assumes that the doping is low, right? So when the doping is low, I can first think about the energy cost of each charge excitation itself.
Okay.
And so in other words, the assumption here is that the doping is so dilute that the interaction between different charge excitation is always small compared to its own energy, cost. So then in this case, I can first ask question: what is the lowest energy excitation? It may be charge or it may be trimer. If it is trimer, then we get the ground state is just formed by an array of these trimers. Yeah.
All right, and I think there's time for one last question from Vala Fatimi.
Yes, I was wondering if there's this unusual sort of form for the superconducting ground state would result in a different, say, some different phenomenology for Andreev reflection processes. I don't know. It's just a sort of random question.
Well, so one thing that is that so here I'm dealing with a case of fully polarized spins, right? So the system is actually spin triplet pairing, right? It's a same spin pairing, so it's very unusual. Let's say very unusual. Yeah. So so this sounds pretty bold, but actually one thing I want to mention is that there's actually recently there's people discuss the possibility of spin polarized superconductivity in trilayer graphene on boron nitride substrate. Sorry, twisted bilayer, right? So some people believe that the superconducting thing there is actually spin polarized. So in this, so that's why I say this mechanism may also apply to other Moiré materials, not just based on TMD, but based on graphene. But what is I think to me what is appealing is that the TMD system is has the simplest kind of electronic structure, right? Just particle in the periodic potential. So that's how we started looking into this. But the mechanism may be more general.
All right. I see no further question. So let us all thank Liang again.
Okay, thank you.
I think this was a great talk. And I hope to see a lot of you here in 2 weeks for the next talk.
Thank you. Yeah.
Well, in 2 weeks, we will have Charlie Marcus giving the seminar.
Okay, wonderful. Bye.
Thank you very much.
Thank you, everyone.